The next speaker today is Donald Youmans, and the title is BF, Schwarzian Theory and Drinfeld-Sokolov Reduction.
Okay, so thank you very much. So first of all, I would like to give a word of thanks to the organizers for organizing this conference despite these difficult situation and circumstances, and of course for giving me the opportunity to present some of my latest work here. And today I want to talk about BF theory, the Schwarzian theory, and how they're related or maybe related via Drinfeld-Sokolov reduction. And this is joint work with Friedrich Wallach. And yeah, so I hope that either tomorrow or yesterday we will see or have seen some formulas which remind you of some formulas I'm going to show today in Anton's talk. So probably I start off with a bit of motivation. So recently there was a lot of interest in BF theory, which I will explain in a second, on a disk, or in our case, we will actually consider the punctured disk, where BF theory is a gauge theory and the gauge group is taken to be PSL2R. And this is because in 2 dimensions, this BF theory with this gauge group encodes basically the first order formulation of certain gravity theories. So in particular, the Jackiw-Teitelbaum gravity theory. And it was shown that somehow on the gravitational side, there was a relation between the bulk gravity theory or BF theory and the so-called Schwarzian theory on its boundary, which was seen to be an effective theory for some of the fields. And so the Schwarzian theory is basically, a theory whose action functional is the integral of the Schwarzian derivative of a certain function. And thus, in particular, it has some kind of SL2R symmetry, and thus was played, or sometimes one could say it's an instant of an ADS to CFT1 correspondence. So from a 2-dimensional gravity theory, which gives some kind of negative curvature, constant negative curvature gravity theory, to so-called conformal theory on the bulk, but in 1 dimension, okay, the role was played by the Schwarzian theory. So we tackled the problem from a slightly different angle because we wanted to look, okay, is there like somewhat natural relation between the BF theory and the Schwarzian purely from the gauge theory part. So we kind of forget about the gravity theory and just look what we can do and if we can do something to obtain actually an effective action on the boundary, which looks like the Schwarzian theory. So the first thing about BF theory is that it's a first order theory. So F is actually the curvature of a certain connection, B a scalar field, and it plays the role of Lagrangian multiplier. And we may add some boundary terms due to the boundary. So if we would then integrate basically over this Lagrangian multiplier, the curvature is set to 0. And thus the whole theory, if we integrate in the bulk, it kind of localizes to the moduli space of flat connection. And what we will do in a second is we will choose boundary conditions such that this moduli space can be actually identified with the space of based loops. So these are basically, if we have our Lie group G here, these are all loops starting and ending at the identity, which can actually be written as this coset space. And it turns out that if we take a loop in here, that this boundary action part, it will reduce to the particle on the group, or this is just the energy functional of a loop. And the observation now is that this base loop space is actually an infinite dimensional symplectic space. And the idea was then to, so what we want to have is kind of the Schwarzian on the boundary. So far we just have a particle on the group on the boundary. But it turns out that this infinite symplectic space admits a nice kind of Lie group action on it, which is Hamiltonian. So there exists a moment map. And thus we can consider its symplectic reduction. So the idea is kind of to do the symplectic reduction of this moduli space. And it turns out that if we do this for the correct group, then this action here, the particle in the group, actually restricted to the reduced space is just the Schwarzian action. So the symplectic reduction here in this case is called Drinfeld-Sokolov reduction. And this the BF theory somehow, through this symplectic reduction procedure of the moduli space, so the configuration space, which we have to integrate in the path integral, gives us the Schwarzian action. So in this way, this is kind of a viewpoint, a geometric viewpoint, purely on the gauge theory part. So to explain the model a bit in more detail, it goes as follows. So we take the gauge group to be PSL2R, and in the field, the BF theory is defined by two types of field connection, so one form and a scalar field. And the action has a bulk part and a boundary part. And the bulk part is just the trace of BF, so B the scalar field and F the curvature. And the boundary part is chosen such that this action actually gives a well-defined Dirichlet problem. So as I said before, this B here, it actually plays the role of a Lagrangian multiplier, which basically localizes everything over the moduli space of flat connections. So any kind of flat connection, and then of course we have to quotient by the gauge group. But what the gauge group is in this case, it's just all gauge transformations which are actually trivial on the boundary. And this is because this boundary term here, this BA term here, is not invariant under gauge transformations, under all gauge transformations. So we have to take kind of this normal subgroup. And we restrict to one more condition, namely that the holonomy of the connection around the circle, so the boundary of the disk, is just the identity. And if we do this, then there's a way to identify this moduli space with the space of based loops. So these boundary conditions, or the boundary term here, are such that A is actually restricted to the boundary, is actually just a B field. And if we then take the equations of motion, F equal to 0, then we can write A in terms of pure gauge, and basically feeding it back into this action part here, there's something like A squared or B, or equivalently B squared. So under using the equations of motion, A being pure gauge, we find the action of a particle on a group. So in the path integral, and this is just basically a summary of what I said before, we have the following situation. We have our path integral of our BF theory, and we integrate out B, the Lagrangian multiplier. We get this moduli space, which we identify with the based loop space, and the action on the boundary, where the action on the boundary, if we parameterize A by pure gauge and use the boundary condition that A is equal to B on the boundary, just gives us the energy functional of the loop. So, or said differently, the particle in the group action. And this is now basically our starting point. Still, the problem is, or the question is, okay, how does the Schwarzian theory even appear? So here we're a priori just having a particle on a group, and okay, it's partition function. So the first thing to do, or to get like an intuition and motivation, is to look at a nice decomposition of PSL2R, namely the Iwasawa decomposition. And here any element can be written as a product of three matrices, where we have an upper triangular matrix, a diagonal one, and a rotation. And then in terms of these fields F, A, and theta, or these coordinates, the action takes a particular form. But more importantly is this last term here. Namely, if we would do an integration by parts, we see that F itself is actually non-dynamical and plays the role of a Lagrangian multiplier, enforcing the constraint that this particular combination in front, 1/2 A squared theta dash, is a constant. And we want to give in the following just various interpretations of this constraint. And why we're interested in this constraint? Well, if we would feed it back into the action, then we see that we can find an effective action which goes as the Schwarzian theory. So it will be the integral over the Schwarzian derivative of a certain function, which is just a tangent of theta over 2. So this is an effective action for theta. So basically here we solve always for A and just substitute back into the action. I just want to make one remark. So we can either see f as a Lagrangian multiplier and integrate it out in the path integral, or we can kind of try to enforce this constraint because we know it gives us kind of what we want from the start. But if we would enforce it from the start, we see that this term basically is a total derivative and hence drops out. So if we enforce this constraint, then we would have to deal with an enhanced gauge symmetry. We will see a nice geometric interpretation of this later on, and where basically we can just shift f. This is just because f doesn't appear in the action no more. And thus we would just have to fix the gauge. Yes, so now another way to see this constraint is as follows. So remember that we started with the action for particle in the group. So G is just a based loop. And now suppose that H is any subgroup of G, and it acts by this cosset space by left multiplication. So here, suppose that we have actually quotient by the right action. So these actions commute. And it basically takes a class and just sends to the class of the product. And if G is just a constant, if H is just a constant, this little h here, then the action is invariant. So we get by Noether's theorem a current, and we could look at this current. So usually to find this current, we suppose that H is local. And if we do so, we see that the change in the action under this multiplication actually gives a quadratic part. So this is just the energy functional for this element H. And something which is linear, which will define us the Noether current. And so of course the question is, or the art is to pick a nice subgroup H, but since we had our Iwasawa decomposition, we have already 3 candidates, and we will stick today to the case where the subgroup is just this upper triangular matrices. And this is a very nice subgroup because then this quadratic part just becomes 0 anyways. So this means that if H is actually local, so this U here would be just a function, the change in the action, well, it just gives us basically the part which will give us the Lagrangian, the Noether current. And in particular, the Noether current is this box here. And by Noether's theorem, we would say, okay, that this is constant. So this is a preserved current. And it's very instructive to just calculate, because we have a explicit decomposition of G and parametrization, how it looks, how this Jn looks in terms of Fa and thetas. And it turns out that if we calculate G prime G minus 1, then by the way, this Jn is just the projection to the lower left corner of this matrix here. So it will be the projection to the lower left corner of G prime G minus 1, so 1/2 A theta dash, which was just the constraint function we've seen, right? So putting Jn to be constant is equivalent actually to the constraint. Which is very nice, because we will see yet another interpretation of this part, or setting this part to a constant. So to sum up a little bit, the observation is as follows. We started with a BF theory, and then we say, okay, we want to constrain the current to get to the Schwarzian theory. And this is just basically by saying, okay, putting this current to be constant. Then we've seen before that we obtained the Schwarzian theory by just restricting the action to the space of based loops, which satisfies that this thing is constant. This combination is constant. So in the path integral, how can we enforce it from the start? Well, we are actually interested in the path integral, which is just the integral over this base loop space here. We have our constraint. We just simply put it in by a delta function, and we integrate the exponential of the action, where this is again the action for a particle in a group. But as I mentioned before, if we put this constraint from the get-going, we will have to take care of a certain gauge symmetry, and the gauge symmetry is basically shifting f in here. So it's shifting f on f plus u. So we just divide basically by this infinite volume. So this means just basically fixing the gauge. And thus, in the end, we obtain an integral over some kind of reduced space of the exponential of the Schwarzian. So the observation now is, of course, we want to see what this reduced space is and if we can find a geometric interpretation of it. And for this, we recall that the base loop space is a symplectic space. And it turns out that actually this constraint, Jn is equal to constant, is actually a moment map. So this Jn, this projection of G prime G minus 1 to the lower left corner is a moment map. And thus, if we have kind of for the Ln action on omega G, but this I will explain in more detail in a second. So the idea is then to see this reduced space as a symplectic reduction of omega G with respect to this moment map given here. Okay, so I just want to recall very briefly the idea of symplectic reduction. So suppose we have a symplectic manifold and some Lie group acting on it, then we can embed the Lie algebra into the vector fields by sending any element to its fundamental vector field. And a moment map basically gives a Hamiltonian for each element x and g, which means it is a function m into the dual of the Lie algebra, which satisfies this moment map condition. Namely, if we contract the fundamental vector field with the symplectic form, then this thing is exact. And the function, the primitive of the exact part is given by the moment map contracted with the element x in G. So in principle, we can just say, okay, if we contract mu and x, since mu takes values in G star and x in G, this will just give us a function on M. And this is the Hamiltonian which generates the G action. So basically it says if we have here this G action, then its flow is kind of defined by a Hamiltonian flow. And the idea of symplectic reduction is that we can use, in good cases, the moment map to generate a new symplectic manifold. And this is also what we've seen yesterday in Anton's lecture. If we say, okay, Q some element in G star, then we can consider the pre-image of Q under this moment map, and we can embed it into the symplectic manifold, which we had before, or we can project it by quotienting out just the stabilizer of this element Q here. And it turns out that this quotient space is a symplectic space whose symplectic form omega reduced satisfies this condition, namely that if we pull back the original symplectic form under the inclusion map, it is the pullback of this new symplectic form under the projection map. So yes, so basically the idea is to take the moment map mu and consider its pre-image of a certain point in G star and quotient by the stabilizer group. So how does it work in our case? So let me recall that we had this Iwasawa decomposition, and now we consider an Ln action, so loops in these upper triangular matrices on the base loop space. And basically this is just given by left multiplication, so it changes f to f plus u. And we said that the base loop space is symplectic, and it turns out that this action actually admits a moment map. And this moment map is given by taking an element G, a base loop, looking at its Marokatan form, and then basically projecting to the lower left corner. So a priori is just basically the projection of this Marokatan form to Ln star. So in terms of this Iwasawa decomposition and the coordinates f, a, and theta, what we've seen before is that this lower left corner of G prime G minus 1 is exactly this combination we've seen so many times before, meaning that the moment maps just sends G to this specific combination. So if we then just, for example, consider the pre-image of, let's say, 1 or any other constant, then these are all based loops such that they satisfy that this linear combination is like this combination, oh, this should be a squared, I'm sorry, is just equal to 1. So these are all those loops which satisfy our constraint, which we were talking about before. The ln action actually preserves the space, and thus we should mod it out. So this ln action preserving the space is what we've dubbed ln gauge symmetry before. And then the reduced space using this ln action admits always a unique representative, a unique class G, or any class G, I should say, admits a unique representative G such that G prime G minus 1 takes this off-diagonal form. And with this off-diagonal form, where we see in the upper right corner already kind of the Schwarzian of the tangent of theta half, it's very easy to find that this energy functional of this specific representative gives us the Schwarzian action. So this is how basically the boundary action just reduces to the Schwarzian action. So in summary, what we had was we started with the BF theory plus certain boundary conditions and the condition that the holonomy of the connection around the disk is trivial. We integrated in the bulk the B field, the Lagrangian multiplier, and got the particle on the group. And then the one idea was basically to constrain a certain current to study actually the partition function of this form, where we have an explicit delta function in here, giving us the constraint. But on the other hand, we could also consider symplectic reduction of this moduli space or configuration space, and it gives us directly kind of the Schwarzian theory. And one can show that under a formal direct calculation, the right-hand side and left-hand side, they just match. So in this way, we can interpret the appearance of this Schwarzian theory on the boundary via symplectic reduction. And the symplectic reduction here, it's called Drinfeld-Sokolov reduction, in particular because here we took the loop group of upper triangular matrices. So just a very quick word towards the end of how to actually calculate this partition function. One idea is that the calculation can be done via localization, but this is actually a formal calculation. So one may take it as probably a definition, but there are many hints that this is a good definition. One subtlety is that this theta was actually a map from S1 into into K, so it should be just into S1. So this is a typo, so it should be just a map from S1 to S1, I'm sorry. So it means that it has winding numbers. And the constraint basically says that theta dash is positive, giving us that the winding numbers should be positive as well. So this partition function after the symplectic reduction, so the reduced partition function is actually a sum over topological distinct sectors. And these that ends, they look as follows. So they're actually integrals over certain orbits, namely exceptional Virasoro orbits, whose points just look like n squared phi dash squared over 2 plus the Schwarzian of phi of x, where phi is a diffeomorphism of S1, and one has to mod out kind of an n-fold cover of SL2R. The L0 here is actually the generating vector field of the S1 action, which just rotates the loop of the diffeomorphism. So it sends phi of x to phi of x plus 1. And this measure here is supposed to be taken as an analog of a symplectic measure. So these kind of integrals we encountered yesterday as well, these are these orbital integrals. But in this case here, one can actually define them by the localization formula of Dustermaat and Heckman, where one just have a sum over all fixed point sets, and one evaluates the exponential at the fixed point, and one has to quotient out by this by the weights of the S1 action. And usually in this setup here, this product will be actually infinite dimensional, so it has to be zeta regularized, for example. And just to say, if beta is the radius, then of the circle, here there's just one fixed point in this case, and it has a specific form. So one can actually calculate it. This calculation was done in the physics literature and also in the math literature before, so it matches. So it hints that this is maybe a good definition. There are certain technical problems, but I don't want to get into them. And just for an outlook, what else can one do? Well, one could, for example, start to study different holonomy restrictions, and this would go from base loop space. So the moduli space then can be identified with other Katsumori orbits, not just the base loop space. Or one could try to study different symplectic reductions and see what we'll have, because here we took the subgroup of G always to be the upper triangular subgroup. And it turns out that if we take any subgroup H, then this LH action will always be Hamiltonian, and the moment map will actually just look the same way. It will be always a projection to LH star. And the third and final question would be, okay, is there actually a gravity interpretation or not? Because, yeah, so far we have not found any. It's not that clear if this has a gravity counterpart or not, but it would be very interesting to study this. So with this, I would like to thank you for your attention.
Thanks a lot, Donald. So please, any questions or comments?
Can I ask a question? So these partition function you computed, so these are characters of Virasoro representations? Or?
Yes, well, they can be related to them. I should put it like this. It's by this orbital integral Kirillov method, basically. Yes, so here we actually get more or less all of them, because we have this sum over the winding numbers, and we have not given interpretation in terms of characters for the moment. But in principle, it should be doable, I think, yes.
But the central charge is 1, or was it?
Actually, here I took the central charge to be 1. Yes, one can make it more general, but then the central charge will appear here, for example, in the exponent, and it can be, yeah, it can be made more general. But for the exposition for today, I took just central charge to be 1.
Okay, thank you.
More questions or comments?
So I wanted to ask you, in this inequality of the partition functions you had in the 2-dimensional and 1-dimensional case, yes, can you see it also on the level of Feynman diagrams, this equality? Or are there any Feynman diagrams for the 1-dimensional case? Actually?
Here, you mean?
I think it was even before. Okay.
Okay, let me just put this here. So I'm not. I think it should be possible to do it via Feynman diagrams. Basically, this okay. Probably I should go here. This may be better. This definition via the Duistermaat-Heckman localization formula is can be, or in the physics literature, can be done via Feynman diagrams as well, where one just basically shows that these higher loop Feynman diagrams, they do not contribute. And basically this Duistermaat-Heckman localization formula in physics says that it's one loop exact. So you compute basically everything up to one loop, and higher loops do not contribute, and then you will get it. So this is kind of the way Witten did it, Witten and Stanford, where they calculated everything on the right-hand side for n is equal to 1, for example. But yes, so they did it via Feynman diagrams and saddle point approximation, while we kind of used as a definition the Duistermaat-Heckman localization formula. But yeah, one has to be a bit careful, because actually in this localization formula, the exponent for the action is not always positive definite. So one would have, if one would like to do the steepest descent method, one would have to kind of deform the contour a little bit such that it will always be positive definite. But this is a technical thing which is still open, how to do this. I think until now it's an open question still. And thus we took it kind of as a definition or an educated guess definition.
Thanks a lot, Donald. I think at this point, we thank you again and wrap up this talk.
Thank you.